Welcome to this tutorial video on ASME Flange FEA Automation. This video describes a novel approach of automating the finite element analysis of an ASME B16.5 raised face, weld neck, bolted flange assembly using ANSYS workbench as the finite element tool. My name is Lotanna and I am a mechanical engineer at Worley. The current industry standard for performing the finite element analysis of a bolted flange assembly is completely manual and takes approximately 3 hours to complete. This manual methodology is tedious and rife with the possibility of mistakes that could happen at any step along the process, such as the CAD modeling, meshing, or boundary conditions definition. However, the new methodology described in this video automated the manual process and therefore eliminated the possibility of errors and significantly reduced the modeling time from 3 hours to just 6 minutes. A significant 97% improvement. The bolted flange assembly could experience various operating conditions during its life cycle, such as normal operating condition, upset condition, startup and shutdown conditions. The normal operating condition is a steady state condition and the most occurring, while the remaining operating conditions are transient in nature and occur sparingly. These conditions produce unique loading magnitudes and sequences. The automation tool I developed performed the finite element analysis of the flange assembly at these operating conditions. The free automation tool provided and also presented in this tutorial was limited to only steady-state finite element analysis. Therefore, it can only be used to analyze the normal operating condition for the 21 flanges highlighted by the red boxes. Here, we have an bolted flange assembly experiencing normal operating condition loads. Therefore, a steady-state thermal and static structural analysis is required to determine the flange seal integrity after applying the loads on the flanged assembly. The flange assembly components consist of two ASME B16.5 raised face, weld neck flange, a 14 nominal pipe size, 600 pounds class rating, and a grooved metal gasket per ASME B16.20. The bolts and nuts properties were selected per ASME PCC1. The properties of each material type assigned to each component was sourced from ASME Section 2, Part D. The steady-state thermal loads applied are listed in the first 8 rows of the table and the static structural loads applied are listed in the remaining rows. A half-symmetry model was used because torsional moments don't significantly affect seal integrity. 3 load combinations were analyzed, the first comprised of only the bolt preload force, the second load combination added the pressure loads to the first load combination, and finally, the third load combination added the thermal loads and moments to the second load combination. This solution section is split into 2 parts. The first part describes the manual process of building the FEA model for a flange assembly, while the second part shows the use of the automation tool to generate the FEA model. The finite element analysis model outlined in the ANSYS workbench application begins with the geometry component where the CAD model is developed. The geometrically accurate CAD model was not required, therefore, the CAD model was decomposed to FEA mesh-friendly sweepable bodies and the nuts geometry replaced with a cylinder of similar volume and surface area. The advantage of this approach was the consistent meshing quality. The geometrically accurate CAD model results in poor quality and inconsistent mesh with Jacobian errors, while the FEA-friendly CAD model results in a better quality and structured mesh. The CAD model was then transferred from the geometry component to the mechanical model. Within the mechanical model component, the material's properties are defined and assigned to the flange assembly components. Next, the coordinate systems, symmetry boundary condition, remote points and contacts were defined. Finally, the FEA model was meshed. The next step in the workbench outline was to link the steady-state thermal component to the mechanical model component. Within this component, thermal loads, such as the ambient temperature, the ambient convection loads for flange, pipe, gasket, bolts and nuts, and the flange bore convection were defined. Finally, the number of steps was defined to reflect the load combinations. In this example we used 3 load steps. The final step in the workbench outline was to link the static structural component to the steady-state thermal component. Within this component, the structural loads, such as the anchor restraint, pressure, pipe end forces and bolt pretension, were applied. Then, the thermal loads were imported from the steady-state thermal component and applied to their respective load steps. Finally, the model was solved, beginning with the steady-state thermal. To recap, the geometry, mechanical model, steady-state thermal and static structural components explained earlier would be automatically generated by the automation tool in 6 minutes. The Run FEA model step isn't automated because the time to completion depends on the computer hardware's quality, therefore, automation provides no benefits. Using the automation tool required just 4 steps. Step 1. Open the ASME bolted flange assembly FEA extension from the ANSYS Workbench ACT start page. Step 2. Define the flange and gasket geometric properties. The bolt and nut properties are automatically assigned per ASME PCC1 standard. The geometry was automatically generated in SpaceClaim. Step 3. Assign the material properties to the flange assembly components. This process takes a bit of time to complete and, behind the scenes, materials XML files are imported into the mechanical model and assigned to each component. Then the coordinate systems, symmetry region, contacts are defined, and finally, the FEA model is meshed. Step 4. Define the thermal and mechanical loads. The steady-state thermal and static structural components are linked and the loads defined. The automation tool took approximately 6 minutes to complete the FEA model as shown by the timer at the top right corner, thereby validating the 97% improvement over the manual process. Other automation tools are available, such as the ASME bolted flange assembly CAD tool, which generates the CAD model for ASME B16.5 and B16.47 bolted flange assembly. Also, the pipe shoe FEA tool that automates the finite element analysis of a welded pipe shoe. And finally the API 579 Part 3 tool that automates the brittle fracture assessment and report generation per API 579 fitness for service code. For questions on these automation tools, please contact me via my email address or my LinkedIn mail, and also check out my LinkedIn profile for articles and resources.